So then there was just one more thing I was going to look at. At the time in class, we had to pause on it because we hadn't done logs, but we've obviously done logs since. So I'm going to have a look here, for example, at question 10. A missile has a 25% chance of hitting a target. So the probability of success, if success is considered a missile hitting its target, is 0.25. Probability of failure is 0.75 as a result. Now, how many missiles must be fired to ensure that there is a greater than 90% chance that the target will be hit at least once? Now, normally we would write down, like for example, if it was 5 coins, we'd write 5 chews. If it was 10 cars, we'd write 10 chews. The problem here is we don't know. We're actually asked how many missiles. So I'm just going to call this X choose. Okay, I'm going to write my success and I'm going to write my failure. Now, how do I know what to put down there? Well, it says it has to be a greater than 90% chance that the target would be hit at least once. Now, at least once is a tricky one to define because we don't know how many times. Like if we knew it was fired 5 times, then we could say, okay, well, at least once means 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. But we don't know in this case what it is. So the best thing we can do, at least once, would be 1 minus never hitting. That makes sense. So if I do a never, that it will never hit the target, so at least once suggests once or more. So I'm going to do 1 minus that it never hits the target at all. So in other words, I'm going to do 1 minus that it never hits, so that's a 0. And I suppose the reason that never hitting, that it doesn't happen, helps us is because now down here, that's going to be 0. And this is going to be X take 0. Now, all of this apparently has to be great. There has to be a greater than 90% chance, so greater than 0.9. Okay, so now what can I do? Well, it shouldn't be too bad because X choose 0. Now, how are we going to do that? Well, go back to numbers that you do know. What if I had 3 choose 0? Well, if I had 3 choose 0, the answer would be 1. What if I had 4 choose 0? The answer would be 1. What if I had 100 choose 0? The answer would be 1. There's only, no matter how many times we shoot the missile, there's only one way to choose none. So that is automatically a 1. Anything to the power of 0 is 1. Now, X take 0 is just X. So what we're actually left with is 0.75 to the power of X for the moment. Now, we want to tidy this up a little bit further. Now, as I said, at the time, I didn't actually do this question with you because we hadn't done logs. Now, why am I suddenly going on about logs? You might be sitting there thinking, I would never have known this was logs. Well, you would now in a second because watch what happens here. So that's 1 by 1 by this. So that's going to be 0.75x. Now, like all maths questions, I really always want to get x on its own. So I'm going to move the 0.9 over, minus 0.9, and I'm going to move the 0.75 to the power of x back, just to tidy that up a little bit. So we have 1 minus 0.9, which would give us 0.1. Now, when we're doing inequalities, we basically treat them as if it was an equal sign. Now, the problem here is, or if you got this far, you'd suddenly realize that you have to use logs because that x is trapped up there in the power. I cannot isolate that x unless I do logs. So how do I do logs? Well, there's kind of 2 ways. You can do the natural log of each side if you want to, but the way we more or less did it in class when we were doing logs was we generally said, okay, well, 0.75 is the base. How do I know? Because we normally call the big guy the base, and then we call the small guy, the x, in this case, the power. So if I want to do log of something to the base, well, clearly the base is going to be 0.75. Now, if my answer is x, well then clearly what goes in here is 0.1. And if you remember when we used to do the snail, we used to go like this. So if you think about doing that the other way around, you would end up back with this, which is what that is. Now I've written an equals instead of an inequality symbol, but just to help us progress. Okay, so I'll just get rid of that. So that is the log version of what you're looking at down there. So again, how did I do that? Well, as soon as I realized it was, and the x was in the power, I knew it was going to be logs. Because 0.75 is the base, when I wrote the log, I put 0.75 as the base. And then obviously we're looking for x, so x is on its own and the 0.1 goes in the other position. Now, underneath the on button on your calculator, you can raise any log to any base. So I'm literally typing in the log of 0.1 to the base 0.75. When I hit equals, I get this. Now, what do we have here? 8.0092 is x. Now, in our case here, so we have 8.00392. So that would suggest you'd need to fire 9 missiles. You'd need to fire 9 of them to make sure, missiles, sorry, I've spelled that wrong, haven't I? To make sure that you would hit the target at least once. I have another one similar to that. Let's look at question 12. Okay, so in question 12, it says, how many times must a fair coin be flipped in order to ensure, now when I talk about a coin, so again, that's definitely Bernoulli, heads or tails, heads or not heads, in other words. How many times must a coin be flipped in order to ensure there is at least a 99% chance of getting at least one tail? Now, this is a very similar type question. So how many times do we flip the coin? So again, this is going to be an X situation. X choose something. Now, success is getting a tail this time. So the probability of success is a half. In other words, getting a tail. And failure, not getting a tail, which really means getting a head, but anyway, not getting a tail is also a half. Now, how do we know what number to put here? Well, it's a similar kind of situation. At least one tail. Now, at least one tail would suggest 1 tail, 2 tails, 3 tails, 4 tails, depending on how many times you flip the coin. So an easier way to do it is to do 1 minus no tail at all. In other words, that it never happened. 1 minus never, like we did up here. So we're going to do 1 minus it never happening. So that's 0. That's going to be x take 0. And we want this to ensure that there is at least a 99% chance of getting. So this has to be bigger than or equal to 0.99. So now let's do what we did before. So anything choose 0 is going to be 1. Anything to the power of 0 is 1. So we end up with a half to the power of x. So we end up with 1 minus, now if I raise 1 to the power of x, it's still going to be 1, because 1 to the raise to the power of anything is 1. So it becomes 2 to the power of x there. Now again, I want to have x's on one side, numbers on the other, so I'm going to actually move him over and move him back. 1 minus 0.99 is going to give us 0.01. Now, because not only is the x stuck in the power, it's also stuck in the bottom. So I'm going to move them up to the top first, and the compensation is negative x. That's okay. Now I'm going to change it all into logs. So what's my base? Well, my base is 2, so that's why the 2 is there. The answer is this, so that goes there. And I'll just use an equals for the moment. And this is going to be minus x. I know that looks a bit strange with the minus, but we'll deal with that in a second. So I'm going to do the log of 0.01. So under the on button, I'm going to do the log of 0.01 to the base of 2. Now the answer I get is minus 6.643856 is equal to minus x. Now they both have a minus, so for that reason, 6.643767. So it says, how many times must a fair coin be flipped? So it would need to be flipped 7 times. in order for us to ensure that we're getting this at least 99% of the time. Okay, so that's it. Hopefully that explains things.